Okay, so today's lecture is regarding combinational circuits using multiple modules. So we are going to now design circuits. Previously in the last class we designed, implemented logic using decoders, multiplexers, ROMs, etc. Today we are going to do the same, except that when we want to implement functions which contain larger number of variables than the size of the modules. The modules themselves may be smaller, and we want to implement functions using larger number of variables. How we can put these modules together to implement circuits with larger number of. And at this stage we will also like to see how actually the practical components look like. These modules, the MSI modules that we talked about, how do they look like? For example, this is an example of designing a 3 to 8 decoder, and a 3 to 8 decoder is going to consist of 3 variable inputs and 8 outputs. So the 3 inputs that we have are A, B and C, and this B and C, so I am going to use two 2 to 4 decoders. So I have one 2 to 4 decoder here and another 2 to 4 decoder over here, and each one of them have 4 outputs. So I have total of 8 outputs, but the 3 inputs that I have, so now apart from the 2 inputs that we showed last time, we also have an enable input. And what this enable input does is, the outputs are enabled only in case this enable input is, in this case, 1. So what happens over here is, this is 0, 1, 2, 3, 4, 5, 6, 7. So 0 to 7, the 8 minterms corresponding to 3 variables A, B and C. So when I want to implement, so I need to have 2 decoders plus an inverter, and this inverter, what it does is, so this A is complemented and fed to this enable E. So when A happens to be 0, then this E happens to be 1, and this decoder is enabled. So what we will have is A0, B0, C0, this output will be valid, or this output will be active. A0, B0, C1, this output will be active. Similarly, so we have 0, 0, 0 to 0, 0, 0, 1, 1, and this is, when A is 1, then this output is going to be active, and so 1, 0, 0 to 1, 1, 1 is going to be correspond to this decoder. So in this way, we can implement a 3 to 8 decoder using this. Similarly, I will show you another example of it, very similar to a 3 to 8 decoder. We are now implementing a 4 to 16 decoder. And in this case, I have 4 inputs, A, B, C and D, which correspond to the 4 variables. And I again have these enable inputs for the decoder. And if I am going to connect the 0 output of this over here, then this will correspond to the 0 output. This corresponds to 3, 4, 7, 8, 11, 12 and 15. So 0 to 15, the 16 minterms corresponding to A, B, C, D will come from 4 decoders. So this type of a logic is called a tree decoding logic, because we have a tree. So if I can, actually I will try show you drawn like a tree, but in this case you can see that this particular decoder is just decoding variables A and B, and is generating the 4 combinations of this 0, 0, 0, 1, 1, 0 and 1, 1. So these outputs correspond to those 4 combinations, and depending on which one is active, one of these output decoders are going to be selected, and depending on which output is going to be actually active depends upon not only the fact that the decoder is enabled, and also the fact that C and D should correspond to the corresponding output. So for example, if I have my input to be 0, 1, 1, 0, this is my ABCD combination. So what's going to happen is, 0, 1 corresponds to this output being active. So this enable will come, and this enable will enable this particular decoder, and now rest of the decoders are disabled, so all these outputs are going to be zeros, 12 to 15, 8 to 11 and 0 to 3, and because this decoder is enabled, and now depending upon if it is 1, 0, see this 1, 0 is going to correspond to 0 0 0 1 1 0. So this particular output will be active, and so I will be able to decode 0 1 1 0 based on this, and rest of this one will be inactive. So that's how you can do this, and the reason it's called, and you can, let's say you're talking of a 6 to 64 decoder, you could be doing this in 3 levels. So you could have first level a 2 to 4 decoder, and then you could have 4 decoders at the second level, and at the third level you could have 16 decoders. So 0 output comes from here, 3 comes from here, and then 63 comes from here, and so on, 60, 61, 62, 63. And the reason it's called a tree decoder is the fact that it's growing like a tree. So this particular output of this is going to enable these, and output of these is going to enable these, 4 of them. And so because I am going to have 16 output, this is how it's going to look like. So I have 2 to 4 decoding, I have 4 to, actually if you consider this together, it's a 4 to 16 decoding, except that the variables I now choose, I have to choose appropriately. So this is, let's say, corresponds to AB. So these are all CD, and these are all EF. Advantage, of course, of this decoder is that I can build a very large decoder using, so in this case I will require 16 over here, 4 over here, and 1 over here, 21 decoders of 2 to 4 to implement a 6 to 64 decoder. But the delays add up, so there is, you can see that the delays are add up logarithmically, just like you have the height of the tree. So in this case the delays are going to add up because there are 3 levels here. So the output of this decoder will take some time to stabilize after the input comes. Typically in such a situation, we assume that all these 6 inputs that we have, they all come simultaneously. In a combinational logic, so these inputs may be coming from some source, but typically we assume that they all arrive together. That means the delays that we are going to have, so this output is going to get stabilized after the decoder delay. This output will stabilize after 2 decoder delays, because this enable has to come and then CD will come. Similarly, this will stabilize after 3 decoder delays, and the decoder delays are adding up. That's a reasonably common way of implementing decoders with multiple levels, and these are called tree decoding circuits. Now let's look at another way of doing decoding. This actually tends to be faster, and because of this reason many times it's implemented using the memory, inside the memory units we try to use this type of a decoding. It's called coincident decoding. What happens over here is we have A, B and CD. So this, what it is showing you is a 4 to 16 decoder. Now 4 to 16 decoder, if we had followed the previous path, we would have required 5 2 to 4 decoders. So instead of that I can do with 2 2 to 4 decoders, but I require some more logic. The logic I require is, if each of this intersection you consider, each of this intersection is an AND gate. So I have 16 AND gates over here, and because I have 16 AND gates, so corresponding to decoding each one of these intersection points. So what happens is, let us say in this case we can consider, let's say I had to do 0 1 and 1 0. So 0 1 is going to make this particular, you can say this is a row, so this is corresponds to 0 1 2 3, and this particular row will be active. And similarly I have 0 1 2 3, and this corresponds to the column, and this particular column will be active. And the AND gate that corresponds to this particular intersection will give me an output 1 because both these inputs are 1. This input is 1 as well as this input is 1. And I would have decoded, so I would have 16 AND gates corresponding to the 16 outputs here. And this is called the coincident decoding. If you compare this tree decoding and the coincident decoding, the difference comes from the fact that here the delays are less. The delays don't add up in the same manner. Because as I said, in many of the combinational circuits we assume that inputs arise simultaneously. So A, B, C, D, all these 4 inputs arise simultaneously. This decoder is acting concurrently with this decoder. The delay that you find over here at this place is the delay of 1 2 to 4 decoder, because at the same time as CD arrived, AB arrived, and this also started decoding, this also started decoding. So basically I have 1 2 to 4 decoder delay plus 1 AND gate delay. And vis-a-vis the tree decoding situation where we have 2 2 to 4 decoder delays, because and here we have 1 2 to 4 decoder delay plus 1 AND gate delay. As typically an AND gate is much smaller delay than a 2 to 4 decoder, this happens to be smaller. And the same logic applies, and when we actually talk of circuits like ROM or RAM, when the address lines that needs to be decoded are very large, today you are talking of decoding 20 lines, 22 lines, each ROM chip or RAM chip can be in megabytes or megabits. So you have a large number of bits to be decoded, and there is a substantial difference in delays between using tree decoding and coincident decoding. So you split the address lines into 2 parts and do the decoding. We will see this later on. So here I want to also talk about one thing about typically when you talk of decoders as practical circuits, or when you go to the lab and look at decoders, so you have the inputs, but many of the time you may have enable inputs shown with a circle over here, which essentially means that this input is active low. That means this particular decoder is going to be activated only when this particular input is low. This essentially shows there is an inverter at the input. Of course, inverter is actually inside the decoder. So when we say this, and then typically we write this input as E bar or enable bar. So basically with a 0 input this will be enabled. Similarly, we also get decoders which outputs are also shown like this. That means this is also an active low. So whatever, let us say if you have an input which is 0 1 and this is 0 1 2 3, so only this particular output is going to be 0, rest of the outputs are going to be 1. So this is how an active low, and assuming that of course this enable input is also 0. So given this is 0 and this is 0 1, this will be the output that you will get. If enable happens to be in this case 1, because it's enable bar, all the outputs will be 1, because it's an active low circuit. Typically you get decoders as active low, both the enable input as well as the outputs. The reason being that typically within the ROM or a RAM, many of the time the decoders are used later, as we will see, for what's called chip selecting these devices. So it's simpler to implement an active low logic as an enabling input. So it is cheaper, and so that is the reason many times decoders also you find are active low outputs. You also get decoders which have multiple enables. You can have this type of a decoder where we have 2 input. So this is E1 bar and this is E2. Yes.
So when the decoder is not activated, the outputs are 1 or they are floating?
1. Okay, the floating point we will come to later. So these decoders are not, they don't have floating output, they are zeros and ones. So that is slightly different. So you also have multiple enable decoders. That means here E1 has to be 0 and E2 has to be 1 for this decoder to be enabled. There is a gating inside, and both these enable inputs are to be, so this has to be made 0, this has to be made 1 for the decoder to be enabled. Of course, a question can be that why does one require this? But we will see that there are situations where you want to enable decoders based on multiple conditions. One could gate these conditions outside and then use the decoder. So it's perfectly fine. So you need to have only one enable. But if you provide for gating inside, it helps. The circuit actually also becomes faster rather than doing the gating outside. Okay, maybe I think I can illustrate this, how this gating inside and outside can make a circuit faster or slower. So if I want to implement this logic, and let us say I have this, and I want to subtract, basically I have, for each of the outputs I have an AND gate, and I have inputs corresponding to this NAND gate. So depending on, let us say if you are talking of 0 0, so I want to decode 0 0. So this is my A B, and I want that this particular output, so only when this is 0, so this particular input has to be again to be 0, so this is E1 bar. So I can have E1 over here, bar here, and E2. So instead of, so I'm not introducing another level. Of course I am having a 4 input NAND gate instead of a 3 input NAND gate, but because I'm not introducing, whereas if I try to do this gating outside, I will have another 2 input NAND or some type of a gate, and output of that will be gated with this. So in this manner, so sometimes you can save some, let's say, make the circuits faster by providing for multiple enables. So let's now talk of the next circuit, which is a multiplexer, and similar to the way that we have in case of decoders, I can also build a larger multiplexer using smaller multiplexers. So the example that I am showing over here is building a 4:1 multiplexer using 3:2:1 multiplexer. Here it's even simpler, we don't even need an inverter. So I need to select based on 2 select inputs. A 4:1 multiplexer requires 2 select lines. So I can have this S0 as a select line, S1 as a select line. This is a 0 input, this is a 1 input, this is a 0 input, this is a 1 input. Again this is a 0 input, this is a 1 input. And I am selecting between 4, let us say X0, X1, X2, X3. And this is my output Y. And you can see that if S0 is, let us say 0, and S1 is, let us say 1, what will happen is S0 being 0, this will be selected over, X0 will be selected here, and X2 will be selected here. But because, so both of them will come over here, this will come here and this will come here, and because S1 is 1, so this is going to get selected, and this is what we are going to get. And this is what we wanted. We wanted 1 0, that is X2 to be coming at the output, and this is how it's going to traverse. So both of them are going to come over here, and so in this case, so it's very clear that the way you can implement a larger multiplexer is having number of levels. Again it's like a tree, of course it's an inverted tree, you're converging. There it was diverging, and here it's converging. So if I'm using a 2:1 multiplexer and I have 3 select lines, I will have 3 levels. If I have 4 select lines, I will have 4 levels. And simply I can implement this. The delays are going to add up, and number of course multiplexers that you require is also going to add up. It's fairly simple to construct such multiplexing trees or decoding trees with any larger decoder or multiplexer. You don't have to start from a 2:1 multiplexer, you can also start from a 4:1 multiplexer. Similarly, you can start from a 3:8 decoder. So it's fairly simple to construct such trees depending upon, of course, what you want to implement and what components you have. So now I will get on to the other point that was raised by a student regarding tri-state. Okay, tri-state buffers are a very important component in today's digital logic. The symbol for a tri-state buffer, okay, oh that's a mistake here, there should be an enable input. It consists of 3 things, 3 terminals, input, output, and an enable. As far as its functionality is concerned, you can just assume that it is like a switch, electronic switch, which is triggered by the enable input. The input to such a circuit is 0 and 1. Output is of course the three possibilities, and that is the reason it's called tri-state. There are three states. The 0, 1, which are the two states typically whether the transistor is on or off, and the other state is the Z state, which is called the high impedance state. So if there is an enable, output is actually going to be nothing but following the input with a small delay, which is the switch delay. But if the enable is not activated, if enable is low in this case, because this is an active high enable input, it is like the switch is disconnected. Okay, what is the implication of switch being disconnected? The implication of switch being disconnected is this particular output is not even defined. And the reason it's called high impedance is it's not being driven by anything. There is no circuit which is driving it. So if there is any other connection, if there is any other value that's going to come here, logic value that's going to come here, that will define that. So it's not being defined by this particular circuit. So such a tri-state buffer is a very useful component, typically for making buses. We can see that we can also do multiplexing with it, and it has a lot of implications because advantages even over using multiplexer, and we will talk about that in a moment. And it's fundamentally behind a lot of circuits, especially microprocessors and peripherals and so on and so forth. So it should be clear that the input takes from the set 0, 1, output takes from the set 0, 1, Z, of course if it happens to be high impedance state if it is not enabled. Many times the outputs are specified to be tri-state, and we will see that how, for example, a tri-state buffer can be used as a multiplexer. If I now want to compare this, so I have two tri-state buffers, and what I have over here is this actually implements a 2:1 multiplexer. Depending upon this select line, if the select line happens to be 0, then this A is going to be, because this enable is going to be active, because the 0 means this is going to be 1, and this particular 1 means this particular A is going to come at the output. If S happens to be 1, then this will be disabled and this will come at the output. Primary thing is, you can actually connect two outputs together of tri-state buffers. Typically for a logic gate, you cannot connect the two outputs together. The reason you cannot connect the two outputs together is one is going to drive the other. If one is at a 0, other is a 1, you do not know what the output is going to be. Whereas here you can connect the two outputs together. Of course, you have to ensure that both these switches are not turned on simultaneously. That is, both these buffers are never activated. That means the enable input to them is mutually exclusive in terms of their dynamic behavior, in terms of the time. So at a point in time when this is enabled, this should be disabled, and when this is enabled, this should be disabled. Of course, this is very nicely ensured by this inverter, which makes sure that one is 0 and the other is 1. There is no harm in having, so then what is the advantage of this? Advantage of such a multiplexing over, of course you can also not just build a 2-to-1 multiplexer, but you can also build a 4-to-1 multiplexer by having or even 8:1 multiplexer by having this separate enables. If you compare this to, let's say, to a typical 4:1 multiplexer where we have 4 inputs and then 2 select lines, the major advantages, and this advantage we will actually, when we start studying about RTL components and buses, this will get re-emphasized. The advantage is I can actually physically remove this without, or add this without making any changes. Logically, of course, I have to ensure that all these 4 are mutually exclusive, because obviously 2 cannot be driving simultaneously this point. But physically, not all 4 of them have to be present, whereas here you have to pre-decide that you need a 4 to 1 multiplexer to be able to select between 1 out of 4. If you have 8 to 1 multiplexer, then you can select 1 out of 8. So this physical multiplexer has to be there, and this particular physical wiring has to be there. Here if it is a bus or if it is a back panel, like typically for example, this is how it works, like in all your PCs, you can put a network card, you need not put a network card, you can put a modem, you need not put a modem. You are not doing any wiring on the board to have these additional components when you insert it. So the back panel that you have where the connector is like a bus, and it is possible to put it or remove it without affecting rest of the circuit. Of course, we do have to ensure that they are mutually exclusive, and that is logically ensured by giving different addresses. But whereas if one has to implement using a multiplexer, you actually need to have physically wires drawn from there, and there is nothing that you can remove in this manner. So that is a very fundamental advantage over using tri-state buffers over something like multiplexers, because in a sense this also implements multiplexing logic, but it provides you a certain flexibility in terms of presence or absence of components. So now let me talk of the same multiplexer, 4:1 multiplexer that we had before, but now I am going to implement it using this tri-state buffer. So I have now another input. So I have this select input that I anyway had, and I also have an enable input. Of course this enable, sometimes you call it chip enable to distinguish between this enable and the decoder type enable. So what it implies is, this particular input, what it implies is, it actually puts the output into the high impedance mode. If this is not enabled, then output will go into the high impedance mode. So now what we have over here is, so I want to, okay, so there is a small mistake over here. You should, I can select between this multiplexer and this multiplexer using one of the select lines. So let us say I use S1 to do this and S0 to select between this. So now if I have X0, X1, X2, X3, I have my input 0, 1, 2 and 3. Now you can see what's happening. If S1 happens to be 0, then this particular multiplexer output, this particular multiplexer output is in the high impedance state, and this output is going to be defined by this. And then of course S0 is going to define, so S0 if it is 1, then this X1 will be selected. So if I have, let us say S0 is 1 and S1 is 0, so then S1 is going to 0, that means S1 is 0, so this particular thing is disabled, so this is actually high impedance state set, and this is going to be 0 or 1, so this particular multiplexer is enabled. And now you have S0 is equal to 1, S0 is equal to 1 is going to select this output, so basically what will come over here is X1. So what I have avoided in this, if you consider the previous 4:1 multiplexer and this 4:1 multiplexer, the difference essentially comes from the fact that I don't need to use another 2:1 multiplexer in the output. And that logic of 2:1 multiplexing is essentially being implemented using these tri-state buffers. This particular S1 is going to select either this multiplexer or this multiplexer, and that's going to decide the whether. So I am doing multiplexing in two ways. One is using the multiplexer, another is using the tri-state buffer. The second level is being implemented using the tri-state buffers. Any questions? Okay, so now let's go to the third component that we wanted to make using multiple modules, and this is a ROM. So I am trying to build a 64:1 ROM using 16:1. A 16:1 ROM will have 4 address lines. So typically when I show a bus, I show this and put a cross and put a 4, which means that it has a width of A3 to A0, and these 4 address lines are going to be common to all of them. And typically ROMs contain, their ROM outputs are tri-state enabled, they are tri-stated outputs. So I have this, I can call it chip enable, these are the chip enables, and because it's 64 into 1 ROM, so this is going to contain 6 address lines. So I can use the 2 MSB address lines A4 and A5 and use a 2 to 4 decoder. Yes. Okay, so we are trying to design a 64 into 1 ROM, and our basic building block is 16 into 1 ROM. So I need 4 of these ROMs, and I take 4 of these ROMs and connect them in this manner. Each of these 16 into 1 ROM has 4 address lines and 1 chip enable. Chip enable essentially is going to define, if chip enable is, let's say, is active, then this output is 0 or 1. If chip enable is inactive, that is chip is not enabled, then output is going to be high impedance. So, and because I am building a 64 into 1 ROM, I require 6 address lines. So I have 6 address lines A4, A5 to A0. So the 4 address lines A3 to A0 I connect to all the ROMs. So this is a sort of a bus which has a width of 4 and it's going to get connected to all 4 of these. And the 2 MSB address lines A4 and A5, I use a 2 to 4 decoder and use the output 0 to 3 to select one of them. So 0 is going to select this, 1 is going to select this, and 2 is going to select this, and 3 is going to select this. Now what happens? Let us say I have my address A5, A4, A3, A2, A1, A0. Some address combination I will take. Let's say this is my address. This A4, A5 is 0 and 1. So the effect of this is this particular decoder output, so this corresponds to 1 output, so this particular decoder output is going to be active and rest of them are inactive. That means rest of these outputs are going to be Z, high impedance. So they are like switches not connected, because this is the only one which can have an output 0 or 1. And now because this is active, and depending upon the address line, so this address line corresponds to 1101, which is D, okay, so in terms of hex, okay, so and this particular location, so of course D is being accessed in all of them, but of course other outputs are not important because their output is Z. So whatever is stored in this location is going to come out over here. Of course it's only 1 bit, so it is going to be whether 0 or 1, whatever is stored here is going to be available here. So what we are talking about is the 6 bits of address lines is going to select out of these 4 ROMs. First of all, these 2 bits are going to select one of the ROMs, and depending upon the location, the actual location is going to be selected by these 4 bits. That particular location is going to be available at the output.
Shouldn't those two be interchanged, A5 and A4?
That's okay. That's just a question of how you interpret it. Okay, 0, 1, 2, 3 I am interpreting. So I am considering this to be the MSB and this is to be the LSB. So 1, order is important in case of a decoder because the way you label the input. So I am labeling the input as 1 and 0. If you label it as 0 and 1, then it's. So in this manner, I can build, of course I can build any size ROM using this. If I want to use a larger ROM, I can use more such ROMs. My basic building block can also be larger. So typically the address lines are connected in this manner. There is something that I want to talk about here, which is an interesting way of looking at address lines. If I talk about, let us say, the same example as before, what happens if I connect A5 to, let us say, A2 here and decode A1 and A0? Take this and connect to the chip enable here, and take this and connect to the chip enable here. So now what's going to happen is, please see that uniquely it's still going to access only one location. It doesn't matter which order you connect the address lines. But as far as what location or where in the ROM it's going to come from is going to get jumbled. So when this is, let us say, 0, 1, so 0, 1 is going to select this. Sorry, 0, 1 is going to get select this. And when I go to the next address for this is 1, 0, that's going to go and select this. And 1, 1 is going to get, so your locations are sort of interleaved now. One location will come from here, another location will come from here, another location will come from here, another location. And then you will go, so if in terms of the address sequence, if you consider, so the locations are going to be, so first location here, second here, third here, fourth here, fifth here, sixth here, seventh. Whereas in the previous case, 16 locations came from this, next 16 from this, next 16. And this is all due to the interpretation of the address lines to be, which is MSB and which is LSB. Otherwise, there is still a unique mapping between an address and a location, except that the location is. There are actually situations, once you study computer architecture, there are some advantages even in interleaving. Of course, not really the scope of, in this course we talk about this. So now let's talk about the ROM itself. So ROM is a fairly important component, and similarly, of course, RAMs we will talk about, they also are very similar, so that's why we discuss this. So I am showing you all the pins of a 2 raised power n into m ROM. So 2 raised power n implies that there is going to be address lines, n address lines, so an minus 1 to a0. And then there is going to be m output lines, y0 to ym minus 1. And typically I have a chip enable bar and I have an output enable bar. The reason that you have provided, so actually they, in case of a ROM, the two act more or less in tandem, like both of them are required. This also has to be 0, this also has to be 0 for the output to be active. If output enable bar is inactive, though the chip may be enabled, but still all the outputs will be in the tri-state. But if both of them are low, then the outputs will be 0 or 1. So the reason for this two inputs is, typically the way the ROM is used is the output is driven by some bus driver, chip enable is driven by some decoder, and you want two conditions. So basically it is a gating of these two conditions to get the output, and that's the reason you have two inputs. And as I said before, doing such a gating has an advantage that you can save on some time. If you do the gating outside, it may be more performance, there may be some delays associated with it. Yes, so as far as a ROM is concerned, effectively you don't see any difference. Both of them, but as far as let us say the implementation internally is concerned, there is an address decoding that is taking place. This address decoding is enabled by the chip enable. To get the proper location or the cell from the ROM that you want to access, you are going to access m bits at a time because it's a 2 raised power n into m, so m outputs are coming. So there will be one cell which corresponds to m bits. A particular address combination is going to access this. So what happens is these address decoders get disabled if the chip enable is not there. If the chip enable is there, of course the address decoders are enabled and you are going to access one cell, but the output is not enabled, so you essentially assume that they are tri-state buffers at the output is not enabled unless the output enable is there. So either one of them is going to put the outputs in the tri-state. So as far as a user is concerned, he effectively doesn't see much difference between CE bar and OE bar. In this case, in case of a RAM, things are different. Okay, we will discuss that. But in this case, there is no difference. But typically, you need two such things to drive a ROM, because there is something called a read bar signal which drives this output, and there is a address decoding which drives the chip enable, and that's the reason we have two different inputs. So we will stop here.